Hello, guys. You're welcome to this lecture. So, in this lecture, we want to review some results from analysis, real analysis. Um, that's because our main focus here is to be able to prove the Picard-Lindelof theorem. We've looked at a version of the theorem. This is a version that we want to prove of the Picard-Lindelof theorem. So that's the ultimate goal for our lecture. All right, for this part of the lesson. But in order to be able to prove it, we need a couple of tools, okay? And some of those tools are outlined here. So we need some information on uniform convergence, basically a review of that from your real analysis course, uniform Cauchy condition of convergence, the Weierstrass M-test. So I'll cover these three for this video. And then I'll do another video where I cover the proof of the theorem itself and then some error estimates of that. So that is the plan for our lesson. Okay. So here's a definition for uniform convergence. I'm sure you've seen this before. The sequence of functions ym of x is said to converge uniformly to a function y of x in the interval alpha beta if for every real number epsilon greater than 0 there exists an integer n such that whenever m is greater or equal to n, then this holds for all x in the interval. Okay, so once you're able to show this, that this is less than epsilon for some m greater than n, then of course you have proved, you have shown that the sequence of functions converge uniformly. Okay, so that's one way you do that. Of course, in this case, the m that you choose or the m that you find here must not be dependent on x. That's one important thing. Okay, so here's an example. This the sequence of functions sine n of x over n, these converge to 0 on R. Okay, and to show that, we basically need to show something like this: yn of x minus 0, because we are saying that it's converging to 0. This is given to you, right? Yn of x minus 0. This is equal to the absolute value of sine n of x over n, but we know that the absolute value of sine or cosine is less than or equal to 1. Therefore, this is less than or equal to 1 over n, right? Which means that, remember that for the definition, I want this to be less than or equal to epsilon. So if, for instance, I take this to be less than epsilon, I can get my n out of that, right? So which means that the absolute value of yn of x minus 0 is less than epsilon for all x in R if I choose n to be greater than 1 over epsilon, right? If I take here this to be less than epsilon and I solve for n, I can show that n should be greater than this, okay? So once again, note that m or n in this case must be independent of x, all right? Okay, so I mean, to see that this actually converge to 0, of course, you can find the limit as n goes to infinity. You can also do a couple of plots, as I have done here, and you actually see that the functions approach 0, right? They all converge to 0 for all values of x. Okay, so for n is 1, this is how the function looks like. For n is 2, you get this purple curve. N is 3, right? And finally, when n is 100, right, this is almost 0, right? So you see that it lies on the line y equals 0 there. Okay. All right. So we have shown that this sequence of functions converge uniformly to 0 just by using the definition. Okay. Now, there are times you can also define uniform convergence using the uniform norm or the sup norm. Okay. And that is what we have here. So the uniform norm or the sup norm of a function f on an interval I is defined by this. Is equal to the sup of x in the interval I, the absolute value of f of x, right? If you like, the maximum value that the function, the absolute value of the function takes. So here's an example. If f of x is equal to x squared, right? Then on the interval -3 to 3, of course, this is the quadratic shaped like this. So at the edges, that's where, when x is -3, you have a 9, you have a 9 there. So the maximum, of course, is 9. Therefore, the subnorm of the function f is equal to 9 on this interval. Well, on all of R, right? On all of R, this is unbounded, right? Which means that the subnorm of f goes to infinity since f is unbounded on R. Okay, on R, I mean, this is going to infinity. Good. Let's look at another example here. Let f of x be the tan inverse of x. Remember, the tan inverse of x, starts from minus, if you like, minus pi over 2, and then all the way asymptotes to pi over 2, right? So it's bounded between negative pi over 2 and then pi over 2. All right. So we know that the absolute value of this is less than pi over 2 for all x in R. And the limit as x goes to infinity of the tan inverse of x is pi over 2, which means that the subnorm of tan inverse of x is pi over 2, right? Okay, there is no number smaller than, if you like, pi over 2. It is the upper limit. Okay, good. So these are two examples of uniform norm. Now we want to look at the uniform convergence with respect to the uniform norm. We've looked at one which is based on the first one based on this definition here, where the absolute value of the functions man of y of x is less than epsilon, right? Now I want to look at a definition that is based on the subnorm. So we say a sequence of functions yn of x converge uniformly to a function y of x or the interval I, all right, if the limit as n goes to infinity of the subnorm, right, or the uniform norm of yn of x minus y of x is equal to that, of course, is equal to 0. So if the limit as n goes to infinity of the subnorm is 0, then we say that the sequence of functions also converge uniformly. So that is another way you can define uniform convergence. So we're going to use that to solve this example here. Yn of x is equal to x squared, right? A sequence of functions. We'll let y of x to be equal to 0, basically the function that it converges to. Then on the interval 0 to 1 over 2, right? In other words, if you pick any value of x in this interval, you can show that y of x converges to 0 for all the values here, right? Now, to do that, we'll take the subnorm of yn of x minus y of x. This is equal to that. On the interval 0 to 1 over 2, right, the absolute value of x to the n, of course, the max in the interval will be 1 over 2, right? We have. So you have 1 over 2 raised to the power n. And if you take the limit as n goes to infinity from the definition, right? As n goes to infinity, know that this is 1 over 2 to the power n. This goes to 0, right? So since this goes to 0, we can conclude that the sequence of functions actually converge uniformly to 0 on this domain, this interval here. Okay. Okay, so that is how you prove uniform convergence. We'll see that if this interval was to extend from 0 to 1, for instance, we are not going to get uniform convergence. So we'll take a look at that. And then I'll show you some graphs of this. Okay. So here you go. However, on the domain from 0 to 1, we have the uniform norm of this, yn of x minus y of x is equal to the sup of absolute value of x to the n. Note that on this interval, right, all the values from 0 all the way until you get to 1 are fine, but at 1, right, where you get your max, at 1, this is equal to 1, which means that the limit as n goes to infinity, remember the definition, right? Limit, if I take the limit as n goes to infinity of this, I get 1, I don't get 0, all right, because of the 1 there. Okay, so because it does not go to 0, which means that on this interval from 0 to 1, the sequence of functions does not converge uniformly, right, to y, where y is 0 in this case. Okay, that is because there is a discontinuity when you hit 1. Okay, so this is important. Why we are interested in uniform convergence. an important feature of uniform convergence is that it preserves continuity. In other words, if you have a sequence of functions that are continuous and they converge uniformly to another function, we'll have a theorem for that. They converge to a function, we can conclude that that function is also continuous. Okay, that's not the case for point-wise convergence. So that's why you're interested in uniform convergence here. Okay, so this is the case, the interval from 0 to 1/2, right? When y is 1, this is a function. When y is 1, you just have this linear graph, right? When, when n is 1. When n is 2, right, you have this quadratic, right? And in the interval, as n is increasing, everything is, all the functions are decreasing uniformly to 0, right? The green one is when n is 10. Okay, you can imagine when you go to n is 100, then it's basically lying on the y = 0 or the x-axis. So they are converging uniformly to 0 for all values of x. Okay, and now on the other case where the interval is from 0 to 1, you see that at 1 you get a jump. At 1 you don't have a 0. At 1 you get a 1. This dot here. Okay, so that is what messes up the uniform convergence of this function on the interval 0 to 1. So in actual fact, from 0 to 1 not included, right? If you don't include 1, if you have 1 with an open bracket, then of course it is uniformly convergent. Okay, that's because if you take the limit as n goes to infinity, you get a 0. Okay, all right. So let's move on to something else apart from uniform convergence. Oh, okay. So let's prove this. If a sequence, all right. So I mentioned this already. If a sequence of functions are continuous, each of them is continuous, right? From a domain A to R, they converge uniformly to A. Okay, so they are continuous and they converge uniformly to a function on A, then that function is also continuous. All right, so you have a sequence of functions, each is continuous, and this sequence of functions converge uniformly to a function f of x, then the function to which they converge is also a continuous function. Okay, that will be important when we come to proving the Picard-Lindelof theorem. That's why we need this. So let's prove this. Now suppose that C is in the domain C, domain A, and you choose epsilon greater than 0. Then for every n in n, right, this n is actually the natural numbers. So for every n in n, the absolute value of f of x minus f of c is equal to absolute value of all of that. Note that this is, the trick. You've probably seen this in real analysis, right? This cancels out this, and this also cancels out this. So in fact, you just have f of x minus f of c, which is equal to this, of course, right? Good. So these are equal. If you use a triangle inequality, then you can bound it. Then this is less than or equal to. Then you can put the bounds on this 2, and then this 2. Okay. Note that this expression here, okay, that's fine. So we'll deal with that. So we have this, and 3 of them. Now, by the uniform convergence of f of n, note that we are told that each of the functions is continuous, and they converge uniformly. So this sequence of functions converge uniformly. If you use the definition of uniform convergence, then we can choose an n, right, in n, such that this function minus the function to which it converges, this f of x here, is less than epsilon over 3 for all x in A. Okay, and for such an n, right, for such an n for which f of n is uniformly convergent, for which this holds, it follows that, okay, don't forget that this thing here, this absolute value here is the same as this. Because of the absolute value, the order is immaterial, right? Also, this as well holds for this. Note that this is just a particular case of this, right? Here we are saying that the X is a C, whereas here is more general. So both this expression here as well as this one, right, will be bounded by that, okay? So we're going to bound this and this by this. So you put in epsilon over 3 here, epsilon over 3 here. When you add them, we're going to get 2 epsilon over 3 that we added to this, okay? Good. So now if you move here, we can rewrite the same thing as, you know, this is the same left-hand side. This is less than, okay, less than because of this, right? Less than, then we're going to plug these guys in there. Less than absolute value of fn of x minus fn c plus 2 epsilon over 3, right? I explained where you get the 2 epsilon over 3 from. Good. Good. Now, we know that fn, each of the functions is continuous. So this is continuous in A. Remember the definition of continuity of real functions, okay? The function is continuous if there exists some epsilon greater than 0, some delta greater than 0, such that fn of x minus fn of c, the absolute value of this, is less than epsilon over 3 if, right, x minus c is less than the delta and x is in A, right? So basically, this is taken from the definition of a continuous function. When we say a function is continuous, this is what it means. You can choose. You can have a delta. There's a delta. For every epsilon greater than 0, there's a delta, which is positive such that this thing holds, and then x minus c less than delta for this. Okay, good. So now this, we can now bound this thing here, this guy, which is what we have here, using the continuity of f and of x. So when we do that and we plug this in here, we get epsilon over 3 plus 2 epsilon over 3, and that is epsilon. Therefore, it means f of x minus f of c is less than epsilon if x minus c is less than delta and x is in A. All right? But again, this means that this function f of x, right, to which all these sequence of functions converge, is continuous, because this satisfies the definition for a continuous function. Therefore, f of x is a continuous function. Okay? Good. So basically, what you should notice is that you've seen this probably in real analysis or function analysis. If you have a sequence of functions that are continuous and they converge uniformly to a function f of x, the function to which they converge is also continuous. That's the main point. Okay? You can look at the details of the proof. Good. Then we want to look at the uniform Cauchy condition. All right? This is a very important condition as well when we come to proving the Picard-Lindelof theorem. So pay attention to this one. So let the function, the sequence of functions f of n, be a sequence of functions that's from A to R. Then this series here, all right, infinite series, converges uniformly on the domain A if and only if for every epsilon greater than 0, there exists an n, a big N, it's a natural number, such that the absolute value, right, of the of this series here, okay, of this series here is less than epsilon for all x, again for all x in A, and all n greater than m greater than n. All right. So for all epsilon that you choose, and there is some n such that for n m greater than this n, you can bound this partial this series. All right. Okay. So this is bounded. In other words, so the gist of it is this: you have a series, right, of functions. All right. You can see that this series here converges uniformly if a partial sum of the series is bounded, okay? And on the other hand, if the partial, all right, is bounded, then you can also conclude that the series itself converges uniformly to some function. Okay, so that is the point here. So what we are going to do is that we are going to show this first, right? We're going to show that if the series converges, then this bound actually holds. This bound is basically a bound for the partial sums, okay? And then on the other hand, we'll show that we suppose that the partial sums are bounded, and if so, then the series is convergent. All right, the series converges uniformly. Okay, so let's define a partial sum Sn of x to be equal to this. All right, we are not going to infinity from 1 to n, right, of this. So we get this. Basically, what we're going to do here is that we're going to rewrite this, this theorem in terms of partial sums, and then we'll prove it from there. Then the sequence of partial sums, Sn, and therefore the series, right, this series here, converges uniformly if and only if for every epsilon greater than 0, there is an n, such that, right, the bound for this partial, the difference between Sn of x and Sm of x is less than epsilon for all x in A and all nm greater than n. Okay? So what I've just said is a rephrasing. I have just rephrased the theorem. We haven't proved anything yet. We just rephrased the theorem to say that what the theorem means is that if the partial sums are less than epsilon, then the series itself, right, infinite series converges uniformly to something. And then we want to show that, on the other hand, if the infinite series converges, then the partial sums are bounded. Okay, so that is a rephrasing of it. Good. Now I want to do part of the proof here. Assuming that n is greater than m without loss of generality, okay, we have that the difference between Sn of x minus Sm of x is equal to this. Basically, n is greater than m, so you can write a partial sum for this as well as for this that includes both n and m. And if you subtract the two partial sums, you get this. You can try that, all right? And this, of course, you can rewrite this as this, okay? And so we want to show that this is less than epsilon. So basically, we put the absolute values, we bound this and bound this. But we know that this is less than, right? We have supposed this now. And then the next round will prove it, okay? So we suppose this is true. If this is true, then of course, the partial sums are bounded. This is less than this. Okay, great. So let's go the other way around. On the other hand, we want to suppose, right? We now want to show that these partial sums converge uniformly to a function. Let's call that s of x. So for all epsilon greater than 0, we want to suppose this is true. All right, we just proved this. Now we're supposing it's true for all nm greater than n for all x in A. Then, for each x, right, for each x in A, the sequence, right, of partial sums is Cauchy, right? In other words, if I choose a particular x, these will just be real sequences. This is a real sequence. That's now, if I choose a particular x, it's a real sequence. A real sequence, you take the difference, and it's always less than this for nm greater than this, then that's a Cauchy sequence. It means that Sn of x is Cauchy, right? It's a Cauchy sequence of real numbers. And so it converges to a function s of x. It converges to s of x also means that the limit as m goes to infinity of Sm of x is this, right? So you choose a particular x, and you can show that, yes, if I choose a particular x, then of course this just becomes a Cauchy sequence. And if a Cauchy sequence is bounded, then of course it converges. Well, the bound shows that it converges to some s of x. Now, for all n greater than m and x in epsilon, right? Remember what it means for uniform convergence. We want to take the limit, right? Remember, if you take the limit as m goes to infinity of both sides of this expression here, right? This guy is convergent, right, for all x. this is converging to some s of x. Okay, and this of course has no m here, so this will remain as that. So when we take the limit, this is s, so that is why we have s of x here, and this is less than or equal to epsilon, which implies that Sn of x, remember this being less than or equal to this implies that the sequence of functions Sn of x converges uniformly to the function s of x on A, and so the series itself. In other words, we have shown that the partial, right, this is a sequence of partial sums. The partial sums converge uniformly, therefore the series itself, that is this, converges uniformly. Okay, so we have proved both sides of the hypothesis of the theorem. Okay, good. So you can go back and review it. In some text, in some books, actually, this is actually written as, you know, as this, the difference between two functions like that. All right, so that is why we rephrase it this way. So you can go back and then take a look at this this definition. Okay, here's a theorem. I haven't proved this, or I haven't shown the proof of this theorem, but it is a theorem that we'll need when we are proving the Picard-Lindelof theorem. So I'll just state it, and then we'll move on to the next thing. I think, which is the Weierstrass. Yes, Weierstrass. Okay, so here, this says that let this Ym be a sequence of a sequence, right? A sequence of functions that converge uniformly to another function y of x in this interval, and let the function f, x of y, be a continuous function in the domain D, such that for all m and x in epsilon, right? For all m, right? If you like a comma here, and x in this interval, these points, right? This sequence of points here are in D. Okay, so x is in this interval, and these are in the domain D. Then this holds. The limit as m goes to a of this integral here is equal to, in other words, I can take this limit inside this integral. As long as this function f here is continuous, and this sequence of functions here are converging uniformly to another function. So if that holds, I can take this limit inside here, and that gives me this. And if I take the limits, right, these functions are converging to y of x. So if I take the limit as m goes to a, right, this one gives me yt, right? So I get this. Actually, I should take m going to infinity here. Okay, good. So this will become useful in our proof of the Picard-Lindelof theorem. So take note of this. Great. Then the last theorem we want to look at in this video is the Weierstrass M test. Okay, that is also extremely useful and important in the proof later on. So we'll prove it. So here this says let this Fn be a sequence of functions, right, from a domain A to R, and suppose that for every n there exists every n in n there exists a constant mn which is greater than or equal to 0, right? So a real number such that the absolute value of this. So each of the functions here is bounded by m. This m depends on the function. All right, so each of them have a different bound. One is bounded by different things. So these functions are bounded for all x in epsilon, and the sum, infinite sum, or this series formed by these bounds here, all right, is bounded. All right, it's less than infinity. So if I sum all of these bounds, all right, that bounded different functions, it is bounded. If this holds, right, if each of the functions is bounded and the series formed from the bounds, right, is also bounded, then this series here of f of n, right, it converges uniformly to some function in the domain A. All right. So once I have a sequence of functions and each of these functions is bounded. That's good. And if I take the individual bounds and I sum them up, and or if you like, if I form an infinite sum or a series of them, and that sequence, that series, if you like, or the sum is bounded, it doesn't go to infinity, it's less than infinity. If that happens, I can conclude that, right, the series of the functions themselves, right, the infinite series of the functions themselves, they converge uniformly through some function in the domain A. Okay, good. So that is the Weierstrass M test. I just have to make sure this is holds, and then I can conclude that the series converges. Good. Now let's prove it. Let epsilon be greater than 0, right? Epsilon be given is greater than 0. Now the Cauchy condition for the convergence of a real series implies that there exists some n in n such that, right, such that the partial sum, right, the partial sum of these bounds is bounded, is less than the epsilon for all n greater than n. Okay, so this says that, note that we are given that this holds. We are also told that this holds, right? In other words, if this infinite sum of mn is bounded, then the partial sum of them is also bounded, right? So partial of them is bounded here. Then for all x in A and all n greater than m, we have this, right? If I bound, that's the bound of the partial of f of x. This is less than or equal to, right? I remove the absolute signs and put them in on the function, right? You've seen this in the integral as well. If the absolute value of the integral is less than or equal to the integral of the absolute of the functions, right? So it's the same here. So this is less than this. And then, but note that we know that the absolute value of f of x is less than the m, right? Here, this is less than mn. So this should be less than or equal to mk here, right? But we also know that the partial sum of this mk is less than epsilon, right? Using the Cauchy condition, right? This infinite sum is less than infinity. The partial sum is less than infinity. So this, of course, is less than this from here. Okay, which means that this series here satisfies the uniform Cauchy condition, right? Theorem 11. So it converges uniformly. Okay. Remember the uniform Cauchy condition says that if I have a series and each of this, right, of the sequence of functions converges, a partial sum of it is bounded. If a partial sum is bounded, then the series itself converges uniformly to some function. Here we have shown that the partial sum of these functions here is bounded. It's less than some epsilon. Therefore, it satisfies that Cauchy condition. And so the series itself, this infinite series here converges uniformly to some function. Okay. So basically that is the Weierstrass test. We'll be using it in trying to prove the Picard-Lindelof theorem. So I'm going to end this video here. When I come back in the next video, I'll try to, we're going to prove the Picard-Lindelof theorem and then do some error estimates and perhaps do some examples as well. Okay. So go over what we've done and then hopefully that will help you to understand better. All right. If you have any questions, of course, let me know. Okay.